Okay, this is section 4.6, and this is going to be part 2. Okay. Oops, it won't let me write up there. That's what I'm doing. 4.6, part 2. Okay, so this is example 2. So once again, it's a maximization problem because if we read it, it says if 1,200 centimeters squared of material is available to make a box with a square base and an open top. Find the largest possible volume of the box and the dimensions, and will give and the dimensions that will give that volume. Okay, so we're trying to maximize volume, so that's our goal. And let me change the ink color here. This doesn't look very dark. The goal is to maximize volume. Okay, so if I draw a picture of this, I start off with a square base. And basically what it says is it says that I have to maximize it. So let me just make this look a little bit better. I'm going to make the square base, and then we have the height of the box. Okay, and I don't know what any of the dimensions are. But if I look at a square base, I know that this is going to be x and x. You know, we'll call that, because square have the same length. So that's why this is x times x. And then let's make the height of it y, because I don't know what it is. So remember, volume of a cube is length times width times height. So right now, I have the length being x, the width being x, and the height being y. Okay, so once again, I have x squared times y. I can't do this because I have two variables instead of one. So like we said before, we have to get this in one variable. So usually that requires us to do a different equation. The other equation that I can use with this, and the goal here is actually the 1,200 centimeters squared. That's telling me that that is area, right? Since we're dealing with a three-dimensional figure, then I'm probably wanting to use surface area for my other equation. And surface area is all the areas of the faces added together. Okay, so the surface area of the bottom of the box is going to be x squared, x times x. And now I'm going to look at the surface area of the sides of the box. So let me use a different color for that. Let's take the opacity down here. Let's use, maybe we can use green or something. Well, let me pick a different color. All right, so let's say I'm looking for one of the sides of the box. Now, if the box has equal height on all sides, I can use a shortcut because the area for one of the sides is x times y, but there's 4 sides to the box. So I'm going to put that all together. One of the areas of the side of the box is x times y, and since I have 4 of those, I get 4x times y. So this is the surface area of that figure. Okay, the surface area was given to us as 1,200, so I get 1,200 equals x squared plus 4xy. And once again, I want to get this in terms of y, because if I could substitute in for y, then I can take the derivative of the function. So what I'm going to do is I'm going to go ahead and move the x squared over, and I get 4xy equals 1,200 minus x squared. Now to isolate y, I'm going to divide both sides by 4x to get 1,200 minus x squared divided by 4x. So now I can sub that in for wherever I see y in the volume formula. So volume equals x squared times 1,200 minus x squared over 4x. Okay, at this point, before I take the derivative, because I'm going to try to simplify this thing down, I'm going to go ahead and reduce it down by simplifying the x squared and the 4x. So if I do that, I can take the x's, I have an x left, so this is going to equal x times 1,200 minus x squared, which gives me 1,200x and that's actually divided by 4, because remember we have the 4 in the denominator, minus x cubed divided by 4. So all I did was I took the denominator and broke it up into 2 pieces. Okay, and I can further simplify this down. 1200 over 4, if I divide that, I get 300x minus 1/4 x cubed. So this is my volume formula. So let me just go ahead and write that down again. So we found the original equation is the volume in terms of x equals 300x minus 1/4 x cubed. Okay, we're now ready to take the derivative. So if I take the derivative of this function, I get 300 minus, bring the 3 down, so we get 3/4 x squared. And that is the derivative. Now to find how to maximize the box, I got to set the derivative equal to 0. So I get 300 equals 3/4 x squared. I'm going to multiply both sides by 4/3. So let me write that out so we can see it. And when I do that, I can take 3 into 300. And that was really thick. Sorry about that. So remember, this was a 3. And this was a 300. So when I reduce it down, I get 4 times 100, which is going to give me 400. And it equals x squared. Okay? So when I solve this, I say x equals plus or minus square root of 400, which equals plus or minus 20. Okay. The negative 20 does not work because remember we're talking about dimensions of a box. So I can conclude that x equals 20. Now remember, this is going to be my critical point. I got to check it. I got to check both sides of it to figure out if I have a maximum or a minimum. So I make up the chart. So 20 is my critical point. And then remember, we're going to use a test point on the left and a test point on the right. We're going to figure out if this is plus or minus. And then we're going to figure out if the function is increasing or decreasing. So on the left, we can pick out a very small value like 0. Although, remember, my dimensions have to be something between 0 and 1200 centimeters squared, or the square root of 1200 if I want to get it into just x. Because remember, this was centimeters squared. So my values of x should be in between the two. So let's pick a very small number like 1. And on the right-hand side, let's pick 21. Just to figure this out. Okay. By the way, your other option was to check your concavity by plugging it in to see if it's plus or minus. You could do that as well. So we're going to go ahead and take the derivative at 1. So remember the derivative formula was 300 minus 3/4, and then we're going to take 1 squared. And remember, this was the derivative at 1. So this becomes 300 minus 3/4. I know that's going to be a positive value, so I'm going to put a plus here. That means my function's increasing. Okay, now I'm going to take the derivative at 21. So taking the derivative at 21, I get 300 minus 3/4 times 21. And that 21 is going to be squared. I'm looking at this, and I know 21 squared is a pretty large number, but we can quickly figure out what it is. 21 times 21. I got 440. Right there alone, if I take 440 and I multiply that by 3/4, the 4s will cancel this out, so I get 110. So this is 330. So you basically have, just to write this down, 300 minus 330, it's going to result in a negative number. So that means that my function is decreasing. So if I put the increasing and decreasing together, we know we have a max, and we can conclude that x equals 20. So let's write that down. So I know the dimensions of my length and my width. You know, the length, which is x, equals 20. And remember, we were in centimeters. And the width, which is also x, also equals 20. So now we have to find the height. Remember, that was y. So remember, we wrote up the function for y, and we said that y equals 1200 minus x squared all over 4x. So we can plug that in. So we get 1200 minus, now remember x is 20, and we're going to square that over 4 times 20. So I get 1200 minus 400 all over 80. 1200 minus 400 equals 800 divided by 80. That will give me 10. So my height, which is my y value, equals 10 centimeters. So my answers are x equals 20 centimeters. That's the length. The width is also 20 centimeters, and the height is 10 centimeters. So you could even write it up like this: 20 centimeters by 20 centimeters by 10 centimeters. And that's my answer.